Okay, this presentation is going to be on gravitation and the moons of the solar system. Next chart, Gary. Hey, like I said before, I think a lot of people would be a little bit surprised to know that for the last over 2,000 years, there have been quite a few different theories of gravitation. Where I started in my listening years with Aristotle, who lived in the 4th century BC, he proposed that objects fall due to a tendency to reach their natural place. Therefore, they fall at speeds proportional to their mass. Go forward to Galileo in 1590, he said something different. He said that he had determined that all objects fall at the same rate regardless of their mass. And in 1687, with the Principia, Isaac Newton said, hold on, I'm going to put this all together in one book, actually 3 volumes. And I'm going to tell you that there is such a thing that's called universal gravitation, which is good not only on Earth, but throughout the universe. When they say that it's an attractive force between all particles proportional to the product of their masses and inversely proportional to the square of the distance between them. And here comes Albert Einstein. He said, no, gravity is not a force. It is a curvature in space-time. Now, you talk about somebody that's thinking outside the box. I think that Einstein certainly did that. At the time, people were befuddled by that. They couldn't fathom how it would be that space-time, which you can't feel, you can't see, you can't smell it, it's just space. How can you curve something that has no matter? Yet, his theory not only showed how you can have that happen, it also showed a reason for the gravitational attraction. If you were to have asked Isaac Newton what causes gravity, he would have just scratched his head and said, I have no idea. Albert Einstein came up with a solution. Let's go to the next chart. So these are the equations for both theories. So on the left is Newton, and on the right is Einstein. Starting off with the field equations, Newton has a gradient there for the acceleration due to gravity, and it's a 3-component vector. So when you look at an equation like that, you're not looking at one equation, you're looking at 3. However, you look at Einstein's field equations, and these are equations because what those involve are second order 4x4 tensors, which means there's 16 equations there. It looks very simple, but it's very deceiving. That's a very difficult set of equations here. Due to symmetry and other things, it turns out that you can eliminate 6 of those equations, so you wind up with only 10. That's a help, but not too much. You go down to the universal law of gravity, which is shown here from Einstein, you got a simple equation over here, which is also 3 equations. What's amazing about this is Einstein's tensors match that law in the extreme. When you have velocities are a lot less than the speed of light, you have what's called a weak gravitational field then, and that weak gravitational field in Einstein's theory reproduces at least the acceleration part of that equation there. If you look also at the constants that are involved, it's kind of interesting here. Newton had one. He called it G. And that G is has a value that it's very difficult to measure. That's probably the least precise number or physical constant that we have, but it's right around about 6.6743 times 10 to the minus 11 meters cubed per kilogram per second squared. Look over here at Einstein's equations, and there's three constants. And what's interesting here is the Einstein gravitational constant contains Newton's gravitational constant. Of all these equations, there is a remnant of Newton still embedded in there because of the fact that these field equations in the limit have to match Newton over here. So it retains that constant. And in addition to it, he has two other constants, the speed of light and the cosmological constant, which he called basically the worst mistake he had ever made in his life. But it turns out that years later, that may be pertinent today. Okay, next chart. So here in a nutshell is a comparison in words of how Newton's theory stacks up against Einstein's theory. Newton said that gravity is a force. Einstein says gravity is a curvature of space-time. Its mechanism is unknown according to Newton. The mechanism for Einstein is the curvature of space itself. Should say space-time. Newton said that gravity is action at a distance. Einstein said no, it's all this is action. All the action is local. Newton said that gravity acts at infinite speed. Actually, Newton didn't say that. It's not in the Principia, but it's implied. Over here, Einstein said no, it acts at the speed of light. Newton said gravity is tied to mass. Einstein said no, gravity is tied to energy. And finally, Newton said space and time are two distinct entities. They're absolute and they're constant. Einstein said no, space and time are one, and they're a unity. They're relative and they're dynamic. It's kind of interesting here that even though Einstein's general theory of relativity has been tested many times and has succeeded every time, it has become the best theory of gravitation that we have. You go to GPL or any place and you ask them, can I see your general theory of relativity equations for sending spacecraft over to Mars? And they look at you and say, what are you talking about? Everybody that works on spaceflight generally works only with Newton's equations. And why is that? The reason is Einstein's equations are easier to understand and use. They're simpler and fewer equations. They're accurate enough for spaceflight, and they have been verified very numerous times. Einstein's theory is a refinement of Newton's laws here. And as a result, if you're going to pick which one to use to come up with a way to get from the Earth to Mars, you're going to look at Newton and his laws. Okay, Gary. So, kind of interesting. You look at those equations, you have to ask, well, how many of these equations have been solved? And for the general case, none of them have. That's true for both Newton and Einstein. We don't have a general equation that you can write down, which when you solve it, will come up with an answer for the trajectory or the motion of particles that you're dealing with. There is no general solution. However, when you look at Newton, there are special cases that have been solved, and especially with the two-body case. When you're dealing with two bodies, like for instance, the Earth and a spacecraft, that has been solved completely. And that is what saved us in trying to get a satellite into Earth orbit and satellites to the planets and to the moon. It's because of that that we can do astrophysics, astrodynamics, I should say. Einstein, on the other hand, it doesn't have any, solutions generally, but there are 3 known cases, special cases that have been solved. Those are the Schwarzschild metric, the FLRW solution, and the Kerr-Newman metric. The FLRW are the initials of the last names of the guys that came up with the theory, with the solution. Schwarzschild was the first. Unfortunately, he was killed in World War I. What a waste. But that is the foundation for cosmology today. Everything, pretty much, most of it, relies on Schwarzschild. Okay, Jerry. Now, I think that Ron knows a little bit about this illustration right here, right, Ron? This is yours, right?
Oh.
Okay, this is from the Principia. This is the book that Einstein, or not, that Newton wrote, where he put in his law of gravity along with the laws of motion. And the solution to the two-body program, or two-body problem, is shown right there. The trajectories that are followed by an object in gravity are basically conic sections. You have circles, ellipses, parabolas, hyperbolas, they're conic sections, and that's the equation. So this illustration on the right basically shows that when you fire an object from a high place on the Earth, depending on the energy that you propel that object at, it'll either follow a conic section and hit the Earth, or if you give it a little bit more energy, it's going to hit the Earth farther away, a little bit more energy, and it's going to go into a circular orbit, even higher velocity than that. You'll go into an ellipse and there on out. Okay, Gary. Now, one thing that a lot of times people will see in these equations is that they look very simple, but what is a lot of times not stated is, like, when you look at the field equation for Newton's theory, the gravitational potential is nothing more than negative g, Newton's constant, times the mass of the body that you're working with, divided by the distance between the body and the object that you're working with. Seems very simple. The thing of it is that's good only for a point mass, or for a body that has uniform density, or density that uniformly is composed of density that is spherically symmetric. If you're dealing with something like the Earth, that is not the equation to use. The equation that we normally use is expanded using gravitational spherical harmonics in there. And what you'll notice in this expansion here is there's a lot of terms that have they all have a term that's called J. J0 times P0 times cosine theta, theta being sometimes it'll be the latitude or the colatitude of the object that you're dealing with. That whole term there is just equal to 1. The second term J1 is 0, so the second term is 0. The first term that's not 0 or 1 is the next object or next term in there, the J2 term. And this can go out to infinity. I think there are some Earth models that go out to like 100 different J terms, I think. I think that JPL may have something that goes out that far. I don't know.
They do, and during the 50s, 60s, that was classified information. Because you could track satellites more accurately if you knew the large case.
And that's the key. Satellites being in Earth orbit, when you track them, you can pinpoint what the values are for each of the J terms in here. Now on Space Shuttle, and I think this is true basically for all launch vehicles, when we did our analysis for astronaut performance, we only went up to J2. J2 is by far the biggest term of all that expansion, and that basically describes an oblate spheroid effect. Oblate spheroid is pretty much a sphere that has been squished down a little bit, so it's bigger around in the equator than it is around in the poles. And that's a very good description for the gravitational field for the Earth. Taking that equation for the gravitational potential out to the J2 term. And that has worked very, very well for us.
So is J3, J4, J5 much smaller than J2?
Much smaller. I think that J3 is something like about 1,000 times smaller than J2. And they generally, there is a somebody that came up with an equation that predicted how, what the trend would be. And when you compare that trend to the actual values that we get from the satellite motions, follows it very well. But they do tail off, and G2 by far is the best, or the highest, biggest. Okay, Gary. So, give you an idea how difficult it is to describe some of the celestial bodies' motions, even with Newtonian physics. This will give you an idea. There's a guy by the name of Charles Eugene Delaunay. He was a 19th century French physicist. He calculated an approximate formula for the moon's motion starting in 1846. He spent most of the next 20 years working on that. He published the results in 2 volumes, one in 1860 and 1867. Each volume was over 900 pages. The second volume consisted entirely of the formula that he can come up with to describe the motion of the moon. What's interesting is his results were checked in the 20th century using computer algebra, and 2 small errors were found. One of those errors was the result of the first error. And that first error was very small. And both of those had negligible effect. But it gives you an idea of some of the very difficult work that was done early on in astronomy when there were no computers.
Very meticulous. Out of 900 pages, out of 1,800 pages, they found 2 errors.
It's just amazing. I just shake my head. I'm glad I'm not an astronomer living in the 16th or 17th or 18th century, Go ahead. Okay, now I'm going to talk about transfers. One thing that you might wonder about is, how in the hell did we get to the moon? If we only have solutions to the 2-body problem that has been solved, and I think at the time of Apollo, we only had a handful of special cases for the 3-body problem, how did we go there? Well, there's something called the Hohmann transfer. It's a transfer from one orbit to another, where you start out, let's say that you're in orbit around the Earth and you want to go eventually to the moon. What you want to do, or what they did, was they broke the problem up into 2 different types of problems. Both of them being two-body problems. The first problem was getting from the Earth to the place where the Earth's gravity meets the moon's, meets the value of the moon's gravity. That follows a Hohmann transfer, which is a section of a conic, section of an ellipse. The second problem that needed to be solved is how do you get from there to an orbit around the moon? And that also was a two-body problem, which was solved. And after exiting Hohmann's transfer, you could easily get into orbit around the moon, but it involved two different impulses. One at the Earth, when it started out on its trajectory to the moon. The second one being when it got to the moon and had to go into lunar orbit. Now there are two other types of transfers that have been developed since that time. One of them is called the low energy transfer. It's a transfer between orbits that allows spacecraft to use significantly less fuel than traditional transfers, the Hohmann being the primary one. But the whole thing here is that by following a low energy transfer orbit or section of an orbit, if you do it properly, you can significantly reduce the second impulse to get into an orbit around the secondary body. There's a subset of that low energy transfer called the ballistic capture transfer, and that's a key one. This is a transfer in which you do start off with one impulse, but you don't need another impulse to actually get into orbit. It would seem to me that would be the primary thing that you want to do. It would eliminate one burn of your spacecraft to get into orbit around the moon. But we didn't know that back in the 1960s. This is something that was developed back in the 1980s. This was after Apollo. But there's two types of these ballistic capture transfers. Talking about the Earth-Moon system, there's an interior type, which is wholly within the Earth-Moon distance, and the exterior one, which goes beyond the Earth-Moon distance. Like I said, this eliminates the second impulse, so you have a true minimum energy trajectory to get from Earth orbit to moon orbit, or from the Earth orbit to Mars orbit. Obviously, the advantages are that it significantly reduces spacecraft fuel and complexity. It increases safety because you don't have to worry about a critical burn at the right time when you get to the moon or Mars. And it's launchable basically anytime. You can launch anytime. When you look at the Apollo missions that went to the moon, they had a particular launch window that they had to meet to get there at the proper time. Because the moon is moving in its orbit, the Earth is moving, rotating and everything. They only had a small launch window in which they could actually launch to make it to the location they wanted to be when they got to the moon. That's not the case for a ballistic capture. Okay, Karen. Okay, now talking about the Apollo missions, this is the trajectory that was flown on Apollo 8. I picked this one because Apollo 8 was the first manned mission that went into lunar orbit. And you can see that initially they were in a circular orbit around the Earth. They then made a burn to get out of that orbit, took them onto a Hohmann transfer. It's called what do they call it here? Translunar coast. And then after it got over here to the moon, you'll notice there's a circle around the moon here. And that is the location of what's called the Hill sphere. It's a location where the moon's gravity exceeds the Earth's gravity. Once you're within that sphere, you're not going uphill anymore. you're now going downhill into the gravity well of the moon. You're picking up speed, and to get into lunar orbit, you have to turn on retro rockets so that you can have the moon actually cover or capture the spacecraft that you want to go into orbit around the moon in. So as you can see, again, this entails two burns or two delta V's, one around Earth orbit, and the other one at the end around the moon. Okay, Gary. So here we come to a very important guy. Let me ask you this, Tim. Do you know or have you ever known or met Edward Del Bruno?
No,
Okay. Do you know about him?
no.
Okay. Now, Edward worked at JPL for a time. I don't know exactly what the years were, but he's very instrumental in this. He was the one that introduced what's called fuzzy boundary theory in 1985. That fuzzy boundary theory was basically a way of getting spacecraft doing a ballistic capture. And the way he first did it, at least for the Earth-Moon case, he would take the trajectory going to the L1 location in the Earth-Moon system, which I'll show you in a little bit. And that, going to that location instead of the moon, that was very fuel efficient, it turns out. The L1 position is basically a parking lot that exists. There's 5 of them. They're called Lagrangian points. But those are parking lots where you can go where the lunar gravity and the Earth's gravity and I think centripetal acceleration basically are in balance. So you can go there and park your vehicle and you can go into a little orbit, but you look inside that orbit, there's nothing there. That would astound, I think, Newton, knowing that you can go into orbit around nothing. Mm-hmm. How do you do that? Ask Albert Einstein, right? Don't ask me. But anyway, it was first used in 1985 to redirect the ISEE-3 spacecraft to rendezvous with the comet Giacobini-Zinner. Then in 1990, he developed a trajectory that parked the Huygens spacecraft, which is a Japanese spacecraft, at the L4 and L5 locations. So, like I said, there's 5 migration points. Now, this is a picture of the book that he had written back in 2004. I highly recommend it to anybody who's interested in finding out how in the hell you go into a ballistic capture. But this covers not only ballistic and low energy trajectories, it also covers chaotic motions. And I don't have any clue about what those are, but all I know is that if you make a very small change at the beginning of your simulation, you can come up with wildly different trajectories than what you would expect by just a small initial change in your values. But anyway, that's a very important book. Now, some of the spacecraft that have actually been on these low energy trajectory, or low energy trajectories are listed right here. I can be the very first one back in 1984. I'm sorry, that was 1991. The IC3 was actually the first one. I don't know why I don't have that on here. But these are the ones, and like I said, I think at the beginning is that some of the spacecraft that have recently been launched to the moon, I think, are following the low energy trajectories, because you look at the length of time it takes them to actually get from the Earth to the moon. They're not on a Hohmann trajectory. I know that for a fact. Okay, Gary. Now, to give you an idea about what these trajectories are like, these are 2 different actual spacecraft that were launched earlier. One is Grail, shown on the left, and the other one is called SLIM, shown on the right-hand side. These are all trajectories that go from the Earth, which is shown in blue in the middle, to the vicinity of the moon, which is basically in the green bands around the Earth there. You can see that these trajectories really go far out. And that's why it takes so long for them to get, from the Earth to the moon. And that is the reason also why these trajectories would not be used for manned flights from the Earth to the moon. But these would be very good trajectories to follow, possibly, for supply ships from the Earth to the moon or from the Earth to Mars. So this I think gives you a feel for what these trajectories are like. They're efficient, but they're slow. Okay, and this is a depiction of the vibration points, and this is the Earth-Sun system here. Sun being in the center, the Earth being over here on the right-hand side, and the moon basically shown here on the upper right of the Earth. But you can get a feel for where these vibration points occur. L1 is between the Earth and the Sun. L2 is behind the moon. You go over here to L3, that's on the other side of the solar system beyond the Sun. I don't think we have any use for the L3. We do have uses for the others. L4 and L5 are basically what you might call Trojan type orbits. They're located about 60 degrees away from the Earth, both behind it and in front of it. I think, if I'm not mistaken, the James Webb Space Telescope, I think, is at L2.
Yes.
Okay, L2. So we have had several spacecraft that have gone to those vibration points. And if you go to the next chart, well, not quite the next chart, yes, but anyway, one of the examples that Ron told me about is called the Artemis-Themis mission. This mission consisted basically of 5 satellites, and those 5 satellites around the moon, around the Earth, had finished their main mission after about a year or so. And it turns out the satellites, at least a few of them, still had quite a bit of fuel left, and I guess it might have been JPL or somebody at NASA was wondering, well, is there a way that we can maybe get those into a more useful orbit? Because one of the problems they had on that mission at the end is that those satellites were spending a lot of time in the Earth's shadow, and they were running out of energy, not out of fuel. So lo and behold, here comes Del Bruno. He said, yeah, I can do something for you. Why don't we take it to L1 and L2? We'll have 2 satellites, one going to L1, one out to L2. And lo and behold, that got approved by NASA personnel. And after 6 months, the spacecraft were put into orbits around the moon with high eccentricity. Apocynthion was 30,000 miles to 18,000 miles. And eventually the Paracynthion was down to 100 miles or less. Let's see. One thing I'll mention here, and I think this is pertinent to what we were talking about last month, Ron, is that the moon is notoriously tricky when it comes to orbits because of its interior composition or distribution of masses. There are what has been called mass cons. These are concentrations of mass within the body. And as a result, I showed you with the potential, the Earth's potential, having all these terms in it. Well, the moon is a lot worse. Even though it's a sphere, it's a nice sphere. I don't think it varies in radius, no matter where you are. But the interior is all messed up, and as a result, it's very difficult to maintain a stable orbit around the moon that lasts very long. And anyway, these tugs that are produced on the spacecraft by those mass cons act on the spacecraft in unexpected ways, which can cause the orbits to be unstable. So let's go to the next one. And this is an example. This is actually the orbits that were taken by the Artemis-Themis spacecraft. L1 is shown on the left. Moon is a lot farther away on the left-hand side too. But one of the spacecraft went to the L2, a libration point. And as you can see, it looks as though those orbits that those satellites are in are orbiting nothing. You look at the inside, you know, you look where L1 is and L2 is, you go there, there's nothing there. And yet you can pretty much say, just looking at a plot like this, that they're orbiting nothing. And that's cool. I think that's really neat. So anyway, this is an example. Let's go to the next chart. This is another example. This is the Genesis mission that was launched some time back, I think probably in the 1990s. And the same thing, very similar anyway. This is the mission that eventually wound up in the L1 orbit over here on the left-hand side. But you can see, even though this is very low energy, the Earth being in the middle, you actually start this from the middle out to the left and then curve around to the right-hand side. That's a very big orbital trajectory that has been found there. Very low energy, but very time consuming. So that's why I say it's not good for a man's flying. Okay, so why did I go through this? Where do these moons come from? Well, that's the question. Look at all the moons. This is just a sample of some of the bigger moons that we have along, you know, in orbit around the planets in the solar system. And they can't come in all sizes, shapes, and forms, and colors, and everything else. And the question is, where do they all come from? So that's what we're going to try to find out using the information I just told you about with gravity. Okay, Gary. Now, just a little bit of a rundown here. Believe it or not, there are now 416 known moons orbiting the planets in the solar system. That is not counting Pluto. There's 600 known moons orbiting asteroids. So there's no more new moons that are known around asteroids than there are around the planets now. So the question still is begging, where the heck did they come from? There's 18 or 19 moons large enough to be gravitationally round. Neptune's moon Proteus is a borderline case, so you don't know whether to count that or not. There are 7 moons that are larger than Pluto, including the Earth's moon. There are 2 moons larger than Mercury. That's Ganymede and Jupiter's Ganymede and Saturn's Titan. And there are 4 moons that have an atmosphere. Primary among them is Saturn's Titan. And Earth, like Tim told us, has 7 known, what I'll call quasi-moons. I'm sure it's probably pronounced quasi-moons.
Wait, quasi is how I've always pronounced it, but who knows what the
But
right
I think a better term would be quasi. A quasi.
crazy.
Okay, and there's an unknown number of mini moons, and there are, I don't know if you know this, but there are 2 ghost moons near the Earth too. These are moons that have been detected but have never been verified, so they're just called ghost moons. But there's something that's called Kordylewski clouds of very small particles that are predicted to have formed in the Earth's vicinity, and those ghost moons may be nothing more than the Kordylewski clouds. Okay, Gary. Now, here's some interesting facts about the moons. I'm not going to go through all these, but to give you an example of how varied these moons are. Did you know that the polar craters on the moon are the coldest places known in the solar system? You don't have to go out to Pluto, just go to the moon. You go to the craters in the south pole of the moon, where they're planning Artemis to go eventually. But that's the coldest place that we know of, except for laboratories here on Earth. Let's see. Ganymede, that's the largest known moon. It's the only moon that has its own magnetic field. Let's see, let's go to another one. Callisto has the most impact craters, and therefore they think that it has the oldest surface of any moon in the solar system. Europa has twice as much water as the Earth. That's a place that NASA is going to be investigating, hopefully in the future. They have an Europa mission plan where they will hopefully find out whether or not there is water ice or water underneath that icy crust that it has. Amalthea is the reddest object in the solar system. J12 is the smallest known moon, only 100 in diameter. Titan is the only moon with an atmosphere denser than the Earth. And not only that, but its atmosphere is like the Earth insofar as it's a nitrogen atmosphere. What's also interesting about Titan is it also has liquid seas, lakes, and rivers, not of water, but methane. Io is very interesting. It's about the same size as the moon. It's so close to Jupiter, I'm sorry, to Saturn, that its tides do not occur in a liquid. They occur on the land, where the land actually rises and falls 100 meters every time there's a tide there. It's incredible. And as a result, Io is the only volcanic moon. It's covered in sulfur, and it has 100 times more lava than the Earth, and it has the highest temperature in the solar system. You would think that Mercury or maybe Venus would have the high temperatures. Don't think of that. Think of Io. It has temperatures over 1,000 degrees centigrade. Incredible. But anyway, it keeps on going. But I think you can get an idea that those are very, very interesting places, just as interesting as the planets themselves.
Actually, Io is Jupiter's moon.
Oh, did I say something else?
It says Saturn here, but it really belongs up in Jupiter.
Oh. You're right. You're right. Hey, you get the $1,000 prize.
Okay, thank you. There we go.
You intentionally put that in there.
Yeah, that's exactly right.
Gary, you know?
Very good, Gary.
Okay.
Well, I do it, I do it in there.
Oh. Okay, so we're getting to the point here where we're trying to figure out how those those moons got to where they are. And here are the theories. Now, even these theories are applicable to all the moons in the solar system. These are the theories that actually were originally thought of for how the moon got into orbit around the Earth. So there's 5 different major theories. First one is called the accretion theory. That came up by Edward Roche back in 1873. He said that maybe the moon was formed with the Earth from the protoplanetary disk by accretion. So they were formed at the same time from the same nebular components. George Darwin, which is the son of Charles Darwin, back in 1879, he said, well, maybe it was fission, where the Earth was rotating originally so fast that the centripetal force threw off a whole bunch of the Earth and formed the moon. And so that was his theory. Another one is the capture theory, and this is the one that I want to explore a little bit more. This one was proposed in 1909 by somebody by the name of Thomas Jefferson Jackson. Now, if you can come up with a more American name than that, let me know. But he said that the moon was formed elsewhere and was gravitationally captured by the Earth. Very interesting. Think of the capture, the ballistic capture theory of Bruno there. The most popular one that we have today is based on the analysis of the lunar rocks that were brought back by Apollo. It's called the giant impact theory, coming up with in 1974, where they say that the moon was formed by debris created by a large object impacting the planet. That object that has been given a name is called Theia. And that is the most popular one today. There is another one that I find very fascinating that has come out subsequent to that. It's called the nuclear explosion theory. 1997, it's claimed that maybe the moon was formed by debris from a nuclear explosion in the Earth. After the Earth was formed, maybe there was a concentration of radioactive substances somewhere in the Earth that reached the explosion point and just blew off a whole bunch of the Earth and formed the moon. I don't believe it, but that is, yeah, maybe. I don't know. But some of the candidates for each one of those are shown down below. As I said, originally these were they came up with these theories for the moon. But you'll notice that the fission one has been completely negated. Nobody believes that today, that the Earth was rotating so fast that it threw off something the size of the moon. And I would think that maybe the last theory there on the nuclear explosion might fit in that same category, but I don't know. Okay, next one. Okay, now look at something that I think is interesting here. If you look at the top of this chart, I show the approximate time that the Earth was formed based on the analysis of Earth rocks. And they have come up with a very, very precise number, 4.5673 billion years ago. Recently, they have also come up with a very fine increment of time in which they think that the moon was formed, 4.51 to 4.53, very short window, billion years ago, which means that the moon apparently was formed somewhere about maybe 40 to 50 million years after the Earth. So you have a little window there for some of the theories to work on. What that window indicates is that the condensation theory, where the planet and the Earth and the moon were formed at the same time, has been thrown out pretty much. Same thing for the fission theory. That was thrown out because of other things too. But because of the very large size of the moon compared to the Earth, it's very unlikely, I think, that it was captured. Just too big of an object for the Earth to capture something like that without the Earth, without the moon or somebody hitting it first. So like I said, the leading theory now is the giant impact theory. Okay, now looking at the other moons, we can categorize them by their orbits. They have been generally divided into what are called regular moons and irregular moons. The regular moons have prograde orbits where if you look from the north, they're going in a counterclockwise motion around the planet. They're pretty much circular, so their eccentricity is very low. They have shorter orbits generally. The irregular moons, however, are distant. They're very long, long orbits, long orbital periods. They're at high inclinations to the planet's equator, high eccentricity, and they're generally in retrograde orbit, which means that their inclination varies from anywhere between 90 degrees and 180 degrees, but they're in stable orbits. Okay, so let's look at those in a little bit more detail. Before we get to that point, there's two different terms that are very similar in definition and are applied to looking at moons that are either that are regular or not regular. Those two terms are the Hill sphere and the sphere of influence. The Hill sphere is the region in which a celestial object dominates the attraction of satellites. And the equation is as shown there. It's an equation where a mass ratio is raised to the 1/3 power. Going down to the sphere of influence, that sphere of influence is an oblate spheroid shaped region around a celestial body where the primary gravitational influence on an orbiting object is that body itself. And that the equation that's associated with that is similar to the other one, but a little bit different. So it's got a mass ratio that's raised to the 4/10 power. Okay, Gary. And so looking at a rundown or tabulation of all the moons and trying to categorize them by their orbits, whether they be prograde or retrograde, regular or irregular. I've shown those for each of the planets that we have. And you see, I think you can see something very interesting here. There's a total of 416 planet. Whoops. Yeah, there's 416 moons around all the planets. Of those 416, 285 are in retrograde orbit. What I find interesting here is that even though they're in retrograde orbit, they're the most populated ones that we have. And instead of being regular, like you might think, they're called irregular. When it comes to regular or irregular, 356 of those 416 are considered to be in irregular orbits. That's 85.6% of all the known planetary moons. One thing I'll point out here is there's usually exceptions to almost every rule, and here's some important ones here. The moon seems to be an exception. It is not usually listed as an irregular satellite, even though its precession is primarily controlled by the sun, not the Earth, and its semi-major axis is only 26/100ths of the radius of the Earth's Hill sphere. So it's very tightly inside the Hill sphere. But on the other hand, its orbit is basically controlled by the sun, not the Earth. So by definition, you might think that the moon might be irregular, but it's usually called a regular moon. Another exception is Triton. That's the largest moon of Neptune. Scientists think that that was likely captured. It's a huge moon. It's the largest one of Neptune, and it's tightly within the Hill radius, but they think it's irregular because of the fact that they think it was captured. So that's an exception to the rule. Okay, next one. And this is a rundown. What's important here, I've listed all the different planets that we have, including Pluto. And I have shown the values for the radius of the sphere of influence on the left, the radius of the Hill sphere for each of those bodies on the right, well, the middle column. And on the right, which is the most important column here, what I have done is I have shown how far inside the Hill radius is for the moon of each planet that is found farthest from that planet. Because if you can show that even the ones farthest from the planet are inside the Hill radius, that then shows that all moons for that planet are inside the Hill radius too. And lo and behold, that's indeed the case. The moon is shown in blue, and that's okay. Moon was shown in blue there, and you can see by the number that I had in there, it's well within the Hill radius for the Earth-Moon system. Okay, So we're finally, I think, at the end. Here's how I think. Now, I have not seen this myself. This is my hypothesis. I don't know if this jives with the current thinking and astrophysics or anything, but based on what I know about the moons in general and Bell Bruno's equations for aero capture and also ballistic capture of objects, here's how I think it's happening. Of those planets that are irregular, I think that small asteroids formed from the protoplanetary disk that wound up in orbits very similar to each of the planets. Some of those would then cross the planet's orbit ahead of the planet, and they would eventually make a pass somewhere down the line where they would come within the planet's Hill sphere. Or the asteroid may have been slowed down when it passed through the planet's upper atmosphere. When you look at the outer planets, they're all gas giants. You got Jupiter, Saturn, Uranus, and Neptune. They all have very thick atmospheres. They're basically balls of gas. So how best to capture a moon except by maybe having a moon pass or skim through the atmosphere and act like a retro rocket to slow the moon down and then eventually get captured by the moon. That's a possibility, and I call that, well, they call that a neural capture. But a capture could also be done by gravity itself by having the moon or the asteroid eventually find itself ahead of a planet, but then also at the same time be within the Hill sphere radius of that planet. And it could then be captured ballistically, no thruster at all, and become a stable, get into a stable orbit. So anyway, you might think that this scenario is has a very low probability, and I agree, but you got to think that what we're talking about are millions of years. The time frame here is not hundreds of years or thousands of years. We're talking about millions or possibly billions of years. The low probability after that length of time can eventually become high probability. And I think that's how maybe some of the moons got to be where they are. So that's it.
Okay.
Yeah.
All right.
Any questions or anything? Anyway, that's the way I see it.
Oh, go back to that last slide, Jerry. That's awesome.
Yeah, that's kind of neat, isn't it?
Different sizes.
Yeah, you can see the difference. See, like I said, if you look at the largest moons, the 5 largest, you got Ganymede, Titan, Callisto, Io, and the Moon. Io and the Moon are pretty much the same size. Io just a little bit bigger, but you can see that these moons that are ahead of our moon are all associated with large planets. Ganymede is Jupiter, Titan is Saturn, Callisto, I think, is Saturn, Jupiter. Yeah, Jupiter, and Io is Jupiter, like I found out from Gary. But the Moon Earth system, the Moon is so big that you can look upon it as a double planet. In fact, my favorite author, Isaac Asimov, back probably about 1970s or so, wrote a book that was called The Double Planet. And he showed in there that, how Earth compared to the other moons and how it then compares to our planet. And a case can be made that Neil did not land on a moon. He landed on another planet, possibly. But I think it's kind of interesting. Of course, this is just a selection of moons. I don't know how they ordered them or anything, but it was by size, obviously. But I don't know if all these are, if there's any missing moons that are not shown.
Yeah. Well, Saturn has like 187 moons now that they've
Yeah, I have that on that one chart.
just,
That's ridiculous, isn't it?
yeah. They said no way for Jupiter to catch up now.
Yeah, it just doesn't seem like that's a case that's gonna happen. Yeah, it's, you look at where those moons are. Um, those moons are all located, like I say, pretty much associated with Jupiter and Saturn. There's also with Uranus and Neptune, but you look at where Jupiter and Saturn are with respect to the asteroid belt, and I'm thinking that, well, maybe the asteroid belt was a lot bigger, and what happened is those big planets, Jupiter and Saturn, scattered those moons around and maybe captured some. I don't know, but that might be an explanation for why they have so many. It's an amazing place that we live in. I think that it'd be very interesting to have a crystal ball to see where we might eventually go as a human race in the future. I suspect that there may be a chance that eventually someday some of these moons may actually be walked on by somebody, from Earth. Who knows?
This is a lot of cool stuff. Thank you.
Yeah, sure. Okay.
Universities have you applied for a professorship?
What I did was I went online to see where Mulberry and Truman went. And I'm thinking about applying there. Yeah. Mulberry and Truman. Now, wouldn't that be something,
Jerry.
on Iowa?
Yes.
You want to use the lights for me?
A microwave on Iowa.
No, it's 100 meters or 100 meters.
Oh,
Yeah. Big, I never saw it come. But it's in a gravitational tug of war, I think, between Callisto and anyway, and it's being flexed by the other. So it's like squeezing the ball.
It's just incredible. One of the things I used to find very interesting opinion by
No problem.
people that.
So you're gonna-
have a permission
Wait,
from-
you gonna be able to come to the meeting? Or-
I'm gonna be in the gym.
Yeah, you can do it.
Going over to Germany. That'd be cool. Got a place to stay then. Whether you like it or not.
Thanks, Gary. Much appreciated.
No problem. Here we go.
If I can survive the trip there.
I have a hard time.